Hi, I'm Eric Paul. I worked with Professor Xiaoping Zhao and Ali this summer with EPSCoR interning. We're working on a wind turbine gearbox simulation, modeling for fatigue life and crack initiation in the gear tooth. So our project is mainly modeling through ANSYS. I'm coding the gear tooth and as well as the gear bearing within the gearbox of the wind turbine, and we're using it to model what the gearbox and the gears and the bearings are, the forces that are facing through real wind conditions. So modeling the gear tooth, we start with the geometry here on the left. As our force is moved across the contact surface right here, as if it's in a chain of gears. And we have boundary conditions along the bottom. And this is all finite element modeling. This is the surface for contact right here, contact surface. And right here is an example of a pressure distribution that we're using, as well as friction forces that are enacted at every node along the pressure contact surface. From this side, here's our gear tooth contact surface and our pressure distribution as well, as it moves along the side here. Shows kind of how we used simple trigonometry to figure out the Fy and Fx directions for our friction forces, and shows how the pressure force distribution is distributed. It's a Hertzian pressure distribution. So once we modeled the gear tooth, we got to analyze the fatigue life with different friction coefficients. So here we have our friction coefficients, our mu from 0 to 0.1, and shows our maximum principal stress and our Tresca, as well as the node location, which is first to fail. And right here you can see, as the friction coefficients are different, the trends stay the same, but our node is receiving more stress as you increase the friction coefficient. This is the shear and this is the Tresca. And then our fatigue life here shows as we increase the friction coefficient, our fatigue life is decreasing incredibly. The next part of the project that I've been working on this summer is the modeling of the ball bearing. So here's the exterior of the ball bearing, and I have a pressure distribution just like the Hertzian distribution in the gear tooth, except right now it's in this little channel within the ball bearing, and it starts at the top here obviously and goes all the way around. So for example, there's this still shot right here, and then another one right here. As you can see, it looks like there's a ball bearing moving through it. So for our bearing analysis, I experimented with a coarse mesh and a fine mesh. That's how many elements you have per unit of space within the ball bearing. And with this coarse mesh, we have a single element contact pressure, so that's without the Hertzian distribution. And you can see there's some noise here on the sides instead of a nice smooth curve like we see in the fine mesh with a 5-element contact pressure distribution. So that shows the importance of the Hertzian distribution, as well as using a fine mesh versus a coarse mesh. This also shows the degrees in which the node on the opposite side of the bearing is enacted. So when we do a final analysis, we'll do the simulation only between this degree range, and we'll have a very high mesh. It'll take a long time, but we'll be able to get very accurate results. Our future works with the ball bearing with friction coefficients and fatigue life estimations. We'll study effects of some natural parameters such as like gust and wind loading as well as modeling the dynamically using LS-DYNA to find real-time stress and strain. We're waiting on some real lab testing to find our pressures. Right now, our pressure is just a set value. We don't know exactly what the pressure is going to be experienced within the gearbox, but once we get that, we'll use that in our simulations. This is made possible by the Iowa NSF EPSCoR grant. Thank you.